Is the universe just a vast, lifeless expanse, or is there something more, something conscious, alive, perhaps even self-aware? Could the cosmos be more than a collection of stars and galaxies scattered across empty space? What if we are all part of a larger mind, an immense cosmic brain, where each galaxy is like a neuron, working in concert with others? Is it possible that consciousness didn't emerge randomly, but was an intrinsic part of the universe from the very beginning? Could our thoughts, emotions, and experiences be tiny reflections of the universe's own awareness? If the universe is indeed conscious, then what role do we play in it? Are we merely observers, or are we active participants, helping the cosmos understand itself? Why do the laws of physics seem so perfectly tuned for life? Could it be that the universe chose conditions that allow consciousness to flourish? And if so, is there a purpose to this grand design? As we gaze into the night sky, are we witnessing the universe looking back at itself through us? If everything is connected, then where does individuality end and universality begin? Do our minds hold the keys to unlock the universe's mysteries, or are we simply parts of a complex, universal mind that has yet to fully comprehend itself? Let's delve into these questions and explore the possibility that the universe might not only contain consciousness, but actually be consciousness itself, pondering its own existence through each of us. The cosmic brain hypothesis. In the vastness of the cosmos, where galaxies stretch like points in an endless web, scientists and philosophers have started to notice a curious pattern, a resemblance between the universe's structure and that of the human brain. The universe, composed of billions of galaxies, seems to be connected in ways that bear an uncanny resemblance to the neural network within our own minds. This similarity has led to a provocative question: could the universe itself function as a kind of brain? When we look at the intricate arrangement of galaxies, clusters, and superclusters in the cosmic web, we see something far from random. Just as neurons in the brain connect through a complex network of axons and synapses, galaxies form connections through vast filaments and dark matter. Italian astrophysicist Franco Vasa and neuroscientist Alberto Filetti conducted a study comparing the structures of the cosmic web and the human brain's connectome, finding striking parallels between the two. Their research showed that while these structures operate on vastly different scales, the patterns and connections share a deep structural similarity. For instance, both brains and the universe show complex networks that follow similar organizational rules, with small, dense nodes connected by long, branching filaments. In the brain, these nodes are neurons. In the universe, they are galaxies or galaxy clusters. This resemblance between the brain and the universe has led to the hypothesis that the universe may function as a colossal brain. In our brains, neurons communicate through electrical signals, building networks that allow for complex thought, emotion, and consciousness. The universe, too, has its form of communication through gravitational forces, electromagnetic radiation, and possibly even dark matter. But does this cosmic network actually process information the way a brain does? And if so, could it be conscious? One theory that supports this idea is panpsychism, the belief that consciousness is a fundamental quality embedded in all matter. Under panpsychism, even particles that make up galaxies could contain some form of proto-consciousness, similar to the rudimentary awareness in simple organisms. This doesn't mean that rocks or stars are aware in the way we are, but rather that they possess a basic form of consciousness that, when combined across the vast networks of the universe, could form a larger, unified awareness. The concept of integrated information theory, IIT, offers another perspective on how the universe might hold consciousness. IIT, developed by neuroscientist Giulio Tononi, suggests that consciousness arises from the degree to which a system can integrate information. In a human brain, this integration happens among billions of neurons connected in a dense network. If we extend IIT to the universe, we might argue that the cosmic web structure could allow for a similar kind of information integration, potentially giving rise to a form of universal consciousness. While this hypothesis remains speculative, it opens up an intriguing possibility that the universe, with its vast network of galaxies and matter, might not only process information but also experience a rudimentary form of awareness. However, While the brain and the universe share structural similarities, they operate on very different scales and with different types of connections. Neurons communicate through electrochemical signals, while galaxies and clusters interact primarily through gravitational forces. Unlike the rapid, continuous flow of signals in our brains, interactions across the cosmos are slow, limited by the speed of light and the vast distances involved. Despite this, some scientists speculate that the presence of black holes at the center of galaxies could serve as focal points in a kind of cosmic communication. Black holes, with their immense gravitational pull, might be compared to neural hubs in the brain, potentially playing a role in the universe's information network. One potential link between brain activity and cosmic activity comes from quantum mechanics. At a quantum level, particles can exhibit entanglement, where two particles remain connected across vast distances, responding instantaneously to each other's states. Some researchers have suggested that this phenomenon, known as quantum entanglement, could represent a form of non-local connectivity that might be essential for a universal consciousness. If such connections exist on a cosmic scale, they might enable a kind of communication across the universe that transcends traditional physical limitations, similar to how the brain's neurons maintain a cohesive consciousness despite being physically separate. Another supporting theory for the cosmic brain hypothesis is the holographic principle, which suggests that all the information in the universe might be encoded on a two-dimensional surface, much like a hologram. If this is true, then our experience of a three-dimensional universe could be a projection of this information. In this sense, the entire universe might be processing information in a way similar to a brain, creating the complex reality we observe. This principle, which some scientists believe could help unify quantum mechanics and general relativity, implies that our reality might be fundamentally informational, with consciousness potentially woven into its very fabric. Philosophical roots, Schrödinger and the unified mind. The idea of a conscious universe might sound like a product of modern theoretical science, yet it has philosophical roots stretching back centuries. One of the most intriguing figures to explore these questions was Erwin Schrödinger, the Nobel Prize-winning physicist whose work extended well beyond the boundaries of quantum mechanics. Schrödinger believed that consciousness is not merely an individual phenomenon confined to the human brain, but might actually reflect a universal, singular mind. This idea was shaped by his fascination with Eastern philosophy, particularly the concept of Atman equals Brahman from Indian Vedantic thought. In simple terms, this notion implies that the self is ultimately indistinguishable from the cosmos or universal reality. To Schrödinger, this was not merely a poetic concept, but a serious philosophical framework that questioned the division between individual minds. Could it be that what we perceive as separate minds are merely facets of a single, unified consciousness? Schrödinger's conviction in a shared mind stemmed from a fundamental question he posed. Why is consciousness only ever experienced in the singular? Throughout his career, he observed that no one experiences more than one stream of consciousness at any given time. This led him to wonder if individual minds might only appear separate due to physical limitations and perception, while in reality, they are connected by an underlying universal mind. The notion of a unified consciousness also addresses an age-old philosophical dilemma, the nature of reality itself. Schrödinger argued that metaphysics, the study of what truly exists beyond our physical world, is not a byproduct of physics, but a foundation that precedes it. In his view, our inability to empirically prove an external world independent of our minds or separate individual consciousnesses is precisely what hints at a singular, interconnected reality. If we are indeed all part of one universal consciousness, it could explain why mind and matter seem intertwined in ways that science has yet to fully unravel. To illustrate his idea, Schrödinger often used the metaphor of a crystal. Imagine a crystal exposed to light, refracting it into many colors. These colors, each distinct, represent individual conscious minds, while the crystal itself symbolizes the singular, cosmic consciousness underlying them all. Though we might perceive ourselves as unique individuals, we are, in this view, different expressions of the same essential consciousness, refracted through various physical forms. Schrödinger's reflections were not widely accepted by Western scientific circles at the time. However, his idea of a single mind has continued to influence both science and philosophy, inspiring researchers to explore consciousness beyond the confines of the individual brain. By suggesting that individuality might be an illusion, Schrödinger opened the door to a profound shift in our understanding of consciousness. If the self is an illusion, then we might be part of a collective experience far more expansive than personal identity allows. Schrödinger's perspective also touches on the relationship between mind and matter. He argued that matter, as we know it, is an objectivation of the unified mind, a way of experiencing the universe through tangible forms and sensations. This framework allowed him to entertain the possibility that physical reality is a simplified projection of a more complex, non-physical realm. In this model, the physical world appears separate and independent because it serves as an interface, like a simplified map of reality for conscious beings to interact with. Scientific possibilities. Conscious agents theory. While Schrödinger's view of a unified mind might sound abstract, modern science has begun to develop theories that bridge these philosophical ideas with empirical science. Among these theories is the concept of conscious agents theory, which explores the possibility that consciousness is a fundamental property arising from the interactions within complex systems. This theory suggests that consciousness isn't exclusive to humans or even biological organisms, but rather can emerge wherever there is enough complexity and connectivity, perhaps even on a cosmic scale. According to IIT, the degree of consciousness in a system can be measured by a metric called phi, representing the system's capacity to integrate information. In theory, if a highly interconnected system like the universe has a high enough phi, it could exhibit characteristics of consciousness. While applying IIT directly to the cosmos is still speculative, it suggests that consciousness may not be limited to biological brains. Rather, it could be a fundamental characteristic that manifests in any system with sufficient complexity, from a single organism to an entire universe. Beyond IIT, Conscious Agents Theory (CAT), introduced by cognitive scientist Donald Hoffman, offers another fascinating approach to universal consciousness. CAT suggests that consciousness is the fundamental building block of reality, and that all physical entities are representations or interactions of these conscious agents. In this view, conscious agents don't emerge from physical matter. Instead, they are primary, and physical reality arises from their interactions. This idea aligns with Schrödinger's concept of a unified consciousness, as it implies that every part of reality, from subatomic particles to galaxies, could be interconnected through a web of conscious experiences. CAT proposes that the universe is essentially a network of interacting conscious agents, with each interaction producing a different aspect of the observable world. Just as neurons in the brain interact to create our experience of consciousness, conscious agents in the universe could interact to generate a form of universal consciousness. In this model, what we perceive as physical reality is simply an interface that allows conscious agents to interact within a shared, structured environment. In other words, reality as we know it could be the product of these conscious interactions, with physical matter and energy as byproducts. While these theories are groundbreaking, they also face considerable challenges, both in terms of empirical testing and philosophical implications. Measuring consciousness in non-human systems, let alone on a cosmic scale, remains a daunting task. Currently, IIT has been applied primarily to biological brains, where we can observe and measure information flow among neurons. Applying it to the universe would require a way to quantify information integration among galaxies or other large-scale structures, a feat that lies beyond our current scientific tools. Nonetheless, conscious agents theory and integrated information theory push the boundaries of our understanding, suggesting that consciousness might not be a unique product of evolution on Earth. Instead, consciousness could be a fundamental aspect of reality itself, arising from any sufficiently complex network. If this is true, it would imply that our universe, with its vast network of galaxies and intergalactic connections, might indeed possess some form of awareness. These theories not only propose a radically new perspective on consciousness, but also hint at a profound interconnectedness underlying all things. In a conscious universe, every action and interaction could contribute to a grander scheme of awareness, where galaxies, stars, and even inanimate matter play a role in the vast tapestry of consciousness. If the universe is indeed a conscious system, then our place in it becomes part of a much larger story, one where each of us may be contributing to the universe's own journey towards self-awareness. Testing the hypothesis: is the universe self-aware? The idea that the universe might be conscious, while fascinating, raises a challenging question: can we actually test this hypothesis? Scientific theories are most valuable when they offer ways to be empirically tested. And while proving universal consciousness is a daunting challenge, researchers are exploring intriguing methods that could bring us closer to an answer. Quantum entanglement occurs when two or more particles become linked in such a way that their states remain interconnected, regardless of the physical distance between them. Some researchers have proposed that these quantum connections could extend on a larger scale, creating a kind of communication across the universe that mirrors the interconnectedness in a conscious mind. If entanglement exists on a cosmic scale, it could provide a mechanism for a unified awareness, enabling instant connectivity across vast distances, similar to how neurons communicate in the brain. Yet another experimental method involves studying large-scale cosmic structures and searching for unexpected patterns or anomalies. If the universe were conscious, we might expect to see evidence of self-organization or purposeful structure beyond what randomness alone would produce. For example, researchers are investigating cosmic phenomena such as dark matter and dark energy, which make up the majority of the universe but remain largely unexplained. It's possible that studying these mysterious components could reveal new insights into the universe's inner workings and hint at an underlying consciousness, if such a concept has any empirical basis. A particularly radical approach involves looking at how we, as conscious beings, interact with the universe. Some interpretations of quantum mechanics, like the von Neumann-Wigner interpretation, suggest that consciousness plays a direct role in determining physical reality, as seen in the observer effect, where particles behave differently when they are observed. If our consciousness can indeed affect the physical universe at a quantum level, this could imply a deep connection between individual minds and a universal consciousness. Researchers could potentially design experiments to explore whether conscious observation has measurable effects on large-scale quantum phenomena, which might reveal a relationship between human awareness and universal processes. While none of these methods can definitively prove universal consciousness, each offers a small step toward understanding the role consciousness might play in the universe. By pushing the boundaries of physics and cosmology, scientists are beginning to develop a framework that could, one day, provide evidence for or against the cosmic consciousness hypothesis. These experimental approaches are speculative, yet they challenge us to think beyond conventional boundaries. While measuring universal consciousness remains a distant goal, these early steps invite us to reimagine what science can achieve. Testing whether the universe is conscious may seem like a bold or even impossible undertaking, but history has shown that the line between science and philosophy often shifts with new discoveries. If future research confirms even the slightest hint of universal awareness, it would fundamentally change our understanding of existence, reshaping the way we see ourselves and our place in the cosmos. Until then, scientists and philosophers alike remain at the frontier of this profound question, seeking ways to probe the unknown and uncover whether the universe might indeed have a mind of its own. The evolution of cosmic consciousness. Could consciousness itself be a journey, unfolding alongside the grand narrative of the cosmos? If the universe indeed harbors a form of awareness, it might not have always existed in its current state. Like stars that are born, shine, and ultimately fade, perhaps consciousness itself evolves, deepening in complexity and expanding in scope over cosmic eons. Imagine consciousness as a seed sown in the fertile ground of the universe's inception, a spark embedded in the very fabric of existence at the moment of the Big Bang. At first, it might have been a mere whisper, a faint awareness of being. But as the universe expanded, forming galaxies and stars, this fledgling awareness could have grown, stretching and evolving with each new astronomical structure that came into existence. In this vision, consciousness is not static. It is shaped by the same forces that govern the stars and planets, flowing and adapting as the universe unfolds. Perhaps, in the early universe, consciousness was primitive and formless, just as simple cells were the early life forms on Earth. But over time, as matter formed into increasingly complex systems from stars to galaxies to clusters, cosmic consciousness, too, may have taken on more intricate patterns, each new formation bringing it closer to self-awareness. As galaxies cluster together, Connected by threads of dark matter like neurons in a vast brain, they may weave a growing web of awareness. Could it be that, with each passing epoch, this consciousness refines itself, developing new layers of complexity, much like a child growing and learning? Does the universe, in its grand age, develop something akin to wisdom, a profound awareness built on aeons of cosmic experiences? The thought beckons further curiosity. If consciousness grows as the universe does, is there a point at which it becomes fully aware of itself? Perhaps consciousness in its primordial form was content simply to exist, much like a dreamer who hasn't yet realized they're dreaming. But what if, one day, it awakens fully an ancient mind, finally grasping the entirety of its own existence? If we, as part of the universe, are milestones in this progression, each conscious mind could be a stepping stone toward this ultimate self-awareness. Every thought we have, every feeling we experience, might contribute to a larger tapestry of understanding within the cosmos. Are we, then, not only witnesses but also catalysts, helping the universe learn what it is and why it exists? In this view, the evolution of cosmic consciousness is a journey from simplicity to profound self-recognition, a journey that spans the birth, life, and eventual death of stars and galaxies. Perhaps, in the end, it is a journey toward unity, where the universe not only understands itself but also finds peace within the grand design it has woven. The universe's capacity for self-regulation and self-awareness. If the universe is conscious, could it also possess an intrinsic drive to balance, protect, and evolve itself, much like the immune system of a living organism? What if, hidden within its cosmic forces, there lies a form of self-regulation, a universal instinct to maintain harmony across its vast expanse? Imagine that, just as the human body fights infection and heals wounds, the universe possesses mechanisms to preserve its integrity. This self-regulation might be subtle, imperceptible to us, but it could be what keeps the cosmic dance in sync, guiding the cycles of creation and destruction with an invisible hand. Black holes could act as cosmic filters, absorbing chaotic energies, while dark matter may serve as connective tissue, holding galaxies together in harmonious clusters. Are these not merely physical phenomena, but aspects of a grand cosmic symphony, ensuring that order emerges from potential chaos? What if this self-regulation leads to something even more profound, self-awareness? The universe, in managing its forces and formations, could be developing a reflective understanding, a way to sense its own existence through the network of galaxies, stars, and perhaps even conscious beings like us. We, after all, are made from its own matter, shaped by its laws, and connected by its essence. If the universe maintains itself, perhaps it also observes itself, each action taken echoing back to shape its evolving awareness. Could it be that each supernova, each spiral galaxy, each black hole serves as a sensor, contributing to the universe's awareness of itself? Just as neurons in the brain process information, cosmic events might communicate something to the larger whole. In this view, the universe not only reacts to disturbances, but also learns from them, refining its self-regulation and nurturing a form of wisdom. If the universe indeed regulates itself, perhaps our consciousness is an extension of its own vigilance, a small part of its vast awareness that has been given eyes to see and a mind to question. Our existence might be the universe's way of observing itself in finer detail, a means for it to ponder its own mysteries and origins through the lens of human curiosity. And so, as the stars align and galaxies drift, as the forces of creation and destruction perpetually balance, we might wonder, are we living within a universe that not only sustains itself but also strives to understand itself? Perhaps this capacity for self-regulation and awareness is leading the universe towards a state of ultimate equilibrium and existence in which it knows itself fully, maintaining harmony in an endless, intricate dance. The role of collective consciousness in the universe. If the universe possesses awareness, could each conscious mind be a vital part of its overarching intelligence, a fragment of a vast collective consciousness? Imagine that we, and all other conscious beings, contribute to a single, boundless awareness, each of our thoughts and emotions rippling outward, merging with the whole. In this vision, consciousness does not exist in isolation. Rather, every mind forms a thread in a larger web, an intricate network spanning galaxies and dimensions. When we think, feel, and experience, we may be adding unique impressions to this cosmic memory, each thought an offering to the universe's growing understanding of itself. Perhaps, like cells in a larger organism, our individual minds gather knowledge, process experiences, and feed them back to the universe, creating a feedback loop of awareness. What if, through this collective consciousness, we help the universe see itself from countless perspectives? Each life, whether human, animal, or something beyond our understanding, could act as a lens, allowing the universe to observe its many facets, comprehend its infinite possibilities. Every moment of joy, pain, discovery, and wonder might contribute to a tapestry of experiences that bring the universe closer to true self-knowledge. If we are all connected within this universal awareness, then our individuality might be an illusion, a temporary separation in service of a greater unity. Perhaps when we empathize, when we connect, we touch this deeper truth, experiencing glimpses of a shared consciousness that transcends our physical limitations. In this perspective, our lives are more than isolated events. They are integral to a grander scheme of understanding, each of us adding richness and diversity to the universe's awareness. And if this is true, then consciousness itself is a powerful force, not confined to the mind, but permeating the cosmos, linking every being in a network of infinite potential. We might ask, are we mere witnesses, or are we collaborators in this universal mind, each of us essential to its self-realization? Could it be that by seeking knowledge, love, and understanding, we fulfill a cosmic purpose, helping the universe comprehend the depths of its own existence through our individual journeys? Perhaps our very thoughts are threads in the fabric of a collective awareness, drawing us all toward an interconnected whole, an infinite consciousness in which we all belong. The convergence of science and spiritual wisdom. As we probe deeper into the mystery of a conscious universe, could it be that science is only now discovering what ancient spiritual traditions have long intuited? Across cultures and centuries, mystics and sages spoke of a cosmos alive with spirit, a vast unity where the boundaries between the self and the universe dissolve. Perhaps modern science is not so much pioneering a new understanding as rediscovering truths woven into the fabric of spiritual wisdom. Imagine that the universe, in its pursuit of self-awareness, has whispered these secrets to countless generations, encoded within the philosophies and sacred teachings of the world. The ancient concept of oneness, found in the Upanishads, Taoist teachings, and indigenous beliefs worldwide, suggests that all existence is interconnected, part of a single, living whole. These teachings may have hinted at a conscious universe long before the notion entered scientific discourse, urging us to look beyond the material and sense the unity beneath. Now, as science advances, it begins to mirror these spiritual insights. The interconnectedness of quantum particles, the strange behavior of matter observed in quantum mechanics, and the structure of the cosmic web all hint at a hidden unity underlying all things. Could it be that science and spirituality, two branches of human understanding, are finally converging? Each from different angles, they lead us toward the same question. Is the universe alive, self-aware, and bound together in a cosmic consciousness? In this union of thought, modern theories like quantum entanglement and the holographic principle become bridges, linking scientific investigation with age-old wisdom. Perhaps the universe has encoded itself in dual languages, one of equations and one of myths and symbols. As we decode both, we come closer to a holistic understanding that neither alone could fully capture. Science, rooted in observation, and spirituality, based in introspection, may together form a fuller picture, illuminating a conscious universe that transcends the physical and the mystical. Could it be that our quest for knowledge is a continuation of this ancient dialogue, a whisper from the universe calling us to remember a timeless truth? In seeking answers, we may be reconnecting with this wisdom, glimpsing a universe that is not only conscious but deeply aware of its unity. And perhaps it is in this convergence where scientific rigor meets spiritual insight that we will find the true nature of existence, an understanding that unites mind and matter, self and cosmos, into a single, boundless awareness. In this view, science and spirituality are not opposing forces but partners in the same exploration, leading us toward a revelation as old as humanity itself, that we are threads in the same cosmic fabric, drawn together by a purpose beyond our understanding, helping the universe know itself. The language of the universe. If the universe possesses consciousness, might it also have a way to communicate a language woven into the very fabric of existence, subtle yet profound? Imagine that every pulse of a quasar, Every gravitational wave, every photon that travels across vast interstellar distances is a message, a glimpse of a hidden syntax that the universe uses to express itself. This language would not be bound by words or symbols, but rather by patterns and vibrations, by the movements of celestial bodies and the resonance of forces we are only beginning to understand. Stars, black holes, and cosmic rays might be its vocabulary, each cosmic event a phrase in an ancient, ongoing dialogue. Could it be that this language is not simply the universe's method of speaking to itself, but also its way of communicating with us, its conscious inhabitants? As we explore the cosmos, our discoveries might be more than scientific breakthroughs. They could be moments of revelation where the universe shares its story. When we observe the spiral of a galaxy or decode the structure of atoms, we might be deciphering fragments of a message that has echoed across time and space, a message waiting to be understood. And quantum phenomena, where particles seem to know they are observed, could be clues that the universe is responsive, shaping its reality based on our awareness. What if our minds too are attuned to this universal language? In moments of insight, inspiration, or profound peace, we may be tapping into a dialogue far beyond our individual thoughts. These experiences might not be random, but are moments when we glimpse the unity of all things. Moments when the universe shares its secrets with those who listen. Have you ever looked up at the night sky and wondered about the secrets it holds deep within its starlit expanse? What mysteries lie beyond the reaches of our sight, waiting to be discovered? Welcome to Unlocking the Universe. 10 mind-blowing cosmic mysteries. In today's journey, we're diving into some of the most astonishing and perplexing facts about the cosmos. From the mind-bending reality of black holes to the enigmatic forces of dark matter and dark energy, the universe is far more mysterious and incredible than we could have ever imagined. So buckle up as we explore these cosmic wonders and unravel the mysteries of the universe one fact at a time. Fact 1. The size of the observable universe. Imagine trying to comprehend the full scope of where we are. It's a challenge that stretches the limits of our minds. The observable universe, the part of the cosmos we can theoretically see from Earth, spans about 93 billion light-years in diameter. But what does that really mean? A light-year is the distance light travels in 1 year, nearly 6 trillion miles. Now, multiply that by 93 billion, and you're just starting to scratch the surface of the sheer scale of our universe. Within this unimaginable expanse, there are at least 2 trillion galaxies, each brimming with millions to trillions of stars, and even more planets. Each light year, each galaxy, represents a part of the universe full of mysteries yet to be explored. And as vast as the observable universe is, what lies beyond is even more intriguing. Because of the finite speed of light and the age of the universe, we can only see as far as light has had time to travel since the Big Bang. What exists beyond this cosmic horizon remains one of the greatest questions in astronomy. Fact 2. Black holes. These are some of the most mysterious and powerful entities in the universe. A black hole is a point in space where gravity pulls so much that even light cannot get out. The gravity is so strong because matter has been squeezed into a tiny space. Most black holes form from the remnants of a large star that dies in a supernova explosion. When the star's core collapses under the weight of its own gravity, it can compress to a point, creating a black hole. In 2019, humanity got its first ever look at a black hole's event horizon, thanks to the Event Horizon Telescope. This image captured a black hole at the center of the galaxy M87, revealing the shadow of the black hole surrounded by a bright glowing ring of light, bending due to its immense gravity. The gravity of a black hole is so strong that it distorts space and time around it. If you were to approach a black hole, you would experience something known as spaghettification, where you'd be stretched into a thin strand of matter due to the gravitational forces. Our very own Milky Way galaxy harbors a supermassive black hole at its center, known as Sagittarius A. Supermassive black holes like this one might play a key role in how galaxies form and evolve over billions of years. Fact 3. Dark matter and dark energy. Though we can see stars, planets, galaxies, and even the light from distant cosmic events, these account for only about 5% of the universe. The rest is made up of dark matter and dark energy, which together compose about 95% of the total mass and energy of the cosmos. Dark matter, making up about 27% of the universe, does not emit, absorb, or reflect light. It neither glows nor can be directly observed, yet we know it exists because of the gravitational effects it has on the visible matter around it. This mysterious substance binds galaxies together and is essential for the structure of the universe. The remaining 68% is dark energy, an even more mysterious force that is driving the accelerated expansion of the universe. Unlike anything else we know, dark energy appears to be a property of space itself. Since the Big Bang, the universe has been expanding, but thanks to dark energy, this expansion is not slowing down as previously thought, it's speeding up. This discovery in the late 1990s has transformed our understanding of the cosmos and its future. The enigmatic nature of dark energy poses one of the biggest questions in science. What is its true nature, and what does it mean for the fate of the universe? Will the universe continue to expand indefinitely, tear itself apart, or eventually stop expanding? Fact 4. The multiverse theory. While our universe is vast beyond comprehension, it might not be the only one. According to the multiverse theory, what we have traditionally called the universe could be just one of countless others in a grander multiverse. This theory extends from ideas in physics that suggest possible multiple universes may arise from the same quantum fluctuations that inflated our own universe. These universes might vary dramatically in their laws of physics, their configurations of matter, and even their fundamental constants. One intriguing version of the multiverse is the many worlds interpretation of quantum mechanics, where every decision creates a new split in reality, leading to new universes for each possibility. Imagine a universe where dinosaurs never went extinct, or where gravity is not a fundamental force. Theoretical frameworks like string theory and cosmic inflation provide some support for the multiverse concept, suggesting that the cosmos might consist of multiple dimensions beyond our familiar three-dimensional space. Each of these dimensions could potentially be a separate universe. The idea of a multiverse pushes the boundaries of our understanding and challenges the very notion of reality. It raises profound questions. If other universes exist, could we ever detect them? And what would this mean for our understanding of existence itself? Fact 5. Neutron stars. Among the universe's most extreme objects, neutron stars are the dense remnants of massive stars that exploded in supernovae. Despite their small size, typically about 20 kilometers in diameter, these stars pack a staggering amount of mass. Imagine the mass of the Sun, over 1 million times the mass of the Earth, compressed into a sphere just 12 miles across. The result is a material so dense that a single teaspoon of neutron star matter would weigh about 6 billion tons. That's equivalent to the combined weight of all humans on Earth. Neutron stars are fascinating not only because of their density, but also their rapid rotation and strong magnetic fields. Some neutron stars spin hundreds of times per second. These stars can also appear as pulsars, which are neutron stars that emit beams of electromagnetic radiation. These beams are only visible when they sweep across the Earth, similar to the light from a lighthouse. Pulsars are so precise in their rotation that astronomers use them as cosmic clocks. Some neutron stars are known as magnetars, which have the most powerful magnetic fields in the universe. These fields are so intense that they can cause starquakes and emit giant flares of energy, which can disrupt satellites and create spectacular light shows in the sky. Fact 6. The expanding universe. Since the dawn of the 20th century, astronomers have understood that the universe is expanding. This was first proposed by Belgian priest and astronomer Georges Lemaitre, and later confirmed by Edwin Hubble, who observed that distant galaxies are moving away from us in every direction. What's fascinating is that it's not just the galaxies moving through space. The fabric of space itself is expanding. This means that, with each passing second, every part of the universe is getting slightly further away from every other part. Scientists measure this expansion using something called redshift. As light from distant galaxies reaches us, it shifts to longer, redder wavelengths as space expands. This shift provides crucial information about the speed of the galaxy's recession due to the universe's expansion. These 6 cubes show the simulated distribution of galaxies at redshifts 9, 7, 5, 3, 2, and 1, with the corresponding cosmic ages shown. As the universe expands, the density of galaxies within each cube decreases, from more than 500,000 at top, left to about 80 at lower right. Each cube is about 100 million light-years across. Galaxies assembled along vast strands of gas separated by large voids, a foam-like structure echoed in the present-day universe on large cosmic scales. This visualization shows the number and clustering of simulated galaxies at different cosmic ages, ranging from 4% to 43% of the universe's current age of 13.8 billion years. Each cube represents a fixed volume of space about 100 million light-years per side. Over the sequence, the expansion of the universe quickly lowers the density of galaxies. Each cube shows a specific cosmological redshift, from 9 to 1, with earlier cubes cast in redder shades. Recent discoveries have revealed that the universe is not just expanding, but it's accelerating. This acceleration is thought to be driven by dark energy, an unknown form of energy that makes up about 68% of the universe. The implications of this expanding universe are profound. If the expansion continues indefinitely, the future of the cosmos could be a big freeze, where galaxies eventually drift so far apart that the stars burn out, leaving a cold, dark universe. Fact 7. The cosmic microwave background. Discovered quite by accident in 1964, the cosmic microwave background, or CMB, is a faint glow of light that fills the entire universe. It is the afterglow, radiation, left over from the Big Bang, and it provides us with a snapshot of the infant universe just 380,000 years after its inception. This cosmic relic was stumbled upon by Arno Penzias and Robert Wilson, who initially mistook it for noise from pigeons in their antenna. Their discovery provided strong evidence for the Big Bang theory, fundamentally altering our understanding of the universe's origins. The CMB is not perfectly uniform. It contains tiny temperature fluctuations that represent the seeds of all future structure, the galaxies, clusters, and vast voids that would eventually form. By studying these patterns, cosmologists can learn about the composition and evolution of the universe. At the time the CMB was emitted, the universe had cooled enough for electrons and protons to combine into neutral atoms, making the universe transparent to radiation for the first time. This moment is known as recombination. Today, advanced satellites and observatories continue to study the CMB to glean more insights into the universe's rate of expansion, the nature of dark energy, and even hints about inflation, a theorized exponential expansion of the early universe that would have happened a fraction of a second after the Big Bang. Fact 8. Life's ingredients are cosmic. It's a humbling and fascinating fact that nearly all elements on Earth were formed in the heart of stars. This cosmic alchemy, where simple elements like hydrogen and helium are transformed into heavier elements, occurs under the extreme pressures and temperatures found in stars. Throughout their lifetime, stars fuse hydrogen into helium, helium into carbon, and so on, up to iron. But the creation of elements heavier than iron requires even more dramatic events, such as supernovae and the collision of neutron stars. When a massive star explodes in a supernova, it releases an immense amount of energy and spews newly formed elements into space. Even gold, platinum, and uranium are forged in these cosmic catastrophes and the cataclysmic mergers of neutron stars. These elements, scattered across the cosmos, eventually coalesce into new star systems and planets, including our own. The carbon in our bodies, the oxygen we breathe, and the calcium in our bones all originated from stardust. So next time you look up at the night sky, remember that we are not just inhabitants of the universe, we are literally made of the universe. Every atom in your body was once part of a star far across the galaxy. We are, in the most literal sense, stardust. Fact 9. Exoplanets and the search for life. Since the confirmation of the first exoplanets in the 1990s, our understanding of the universe has expanded dramatically. To date, thousands of planets have been discovered orbiting stars outside our solar system. These exoplanets come in a fascinating array of sizes, compositions, and orbits. Among these, some are eerily similar to Earth, with conditions that may support life. Scientists use advanced telescopes like Kepler and test to detect these distant worlds by watching for the slight dimming of a star as a planet passes in front of it, a method known as the transit method. Particularly exciting are those exoplanets in the habitable zone, a region around a star where conditions might be right for liquid water, a crucial ingredient for life, as we know it to exist on the surface. The quest to find extraterrestrial life is intensifying. Future missions plan to analyze the atmospheres of these exoplanets, searching for signs of life such as oxygen, ozone, and methane. Such discoveries could answer one of humanity's oldest questions: are we alone in the universe? Every new exoplanet discovered broadens our perspective, reminding us of the vast possibilities that lie beyond our home planet. As we continue to explore, we not only learn more about the universe, but also about the potential for life's diversity beyond Earth. Fact 10. The youngest galaxies. By peering deep into the cosmos, astronomers are not just looking out in space, they are also looking back in time. Using powerful telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope, scientists have been able to observe galaxies as they existed just a few 100 million years after the Big Bang. These observations are crucial because they show us the earliest stages of galaxy formation. The youngest galaxies are often small, irregular, and highly active, quite different from the large, well-structured spiral and elliptical galaxies we see in the nearby universe. Studying these young galaxies helps us understand how galaxies grow and evolve. For instance, we see that early galaxies were often much more chaotic, with high rates of star formation and frequent collisions that eventually led to the large, organized structures of stars we are familiar with today. These galactic youths are not just random patches of stars, they are the building blocks of today's universe. Observing them offers clues about the fundamental processes that have shaped everything we see around us, from the distribution of galaxies to the very structure of the cosmos. As technology advances, we will continue to push the boundaries of what we can observe. Each new discovery not only helps us piece together the cosmic puzzle, but also connects us more deeply with the origins of our own galaxy and ultimately, our place in the universe. From Einstein's theory of relativity to the mind-bending mysteries of quantum mechanics. From the explosive origins of the Big Bang to the eerie invisibility of dark matter, these ideas are not just theories. They're gateways to a universe beyond imagination. But what if there's more? What if our universe is just one of many? Or brace yourself, what if we're all living in a simulation? Embark with us on a journey to uncover the universe's greatest mysteries, diving into mind-bending theories that will expand your imagination. Together, we'll travel through the cosmos, unlocking the secrets of existence. Theory of relativity. Developed by Albert Einstein in the early 20th century, this theory reshaped our understanding of space, time, and gravity. It's divided into two parts: general relativity and special relativity, each revealing unique insights about the universe that continue to shape science today. Let's dive into general relativity, introduced by Einstein in 1915. Unlike earlier concepts of gravity as a force acting across space, general relativity describes gravity as a result of curvature in the fabric of space-time. Picture a stretched-out trampoline with a heavy ball in the center. The weight of the ball creates a dip, causing smaller objects to move toward it. In the same way, massive objects like stars and planets create similar dips in space-time, which draws other objects toward them. This is how general relativity redefines gravity as the bending of space and time itself. This idea of space-time as a four-dimensional entity where mass and energy can cause a curvature was groundbreaking. The closer an object is to a massive body, such as a planet or a star, the stronger the gravitational effect it feels due to this curvature. In 1919, general relativity received its first experimental confirmation during a solar eclipse. astronomers observed that starlight passing close to the sun was bent, just as Einstein had predicted. This phenomenon, known as gravitational lensing, occurs because massive objects, like the sun, bend the space around them, causing light to follow a curved path. Today, gravitational lensing remains a valuable tool in astronomy, allowing scientists to study distant galaxies and even detect objects that would otherwise be invisible. The implications of space-time curvature are profound. For example, in areas where mass is exceptionally dense, such as in black holes, space-time curvature becomes so intense that it collapses into what's known as a singularity, where gravitational forces become infinitely strong. At a singularity, the known laws of physics break down, creating an area where even time may cease to exist as we understand it. Einstein's equations in general relativity also hinted that the universe could not be static, eventually leading scientists to discover the expansion of the universe and support for the Big Bang theory. This concept is foundational in cosmology and helps us understand the vast structure of the universe. Moving to special relativity, which Einstein introduced in 1905, we encounter another revolutionary idea. The speed of light is constant, regardless of the motion of the observer or the light source. Special relativity specifically applies to objects moving at constant, non-accelerating speeds and fundamentally changes how we understand time and space. According to this theory, as an object nears the speed of light, time slows down for it relative to an outside observer. This phenomenon, called time dilation, has been observed in experiments where fast-moving particles and clocks flown around Earth experience measurable time differences. For example, GPS satellites in orbit need corrections for time dilation to maintain accurate navigation on Earth. Two critical concepts arise from special relativity: time dilation and length contraction. Time dilation means that time slows down for objects moving at high speeds. This could theoretically allow for long-distance space travel, where astronauts could experience only a few months while years pass on Earth. Length contraction, on the other hand, states that objects in motion appear shorter in the direction they are moving. This effect is only noticeable at speeds close to the speed of light, making interstellar distances appear shorter for high-speed travelers. Together, these concepts reshape our understanding of time, space, and even the feasibility of human space exploration. One of the most famous outcomes of special relativity is the equation E equals mc squared, which reveals that energy is equal to mass times the speed of light squared. This equation implies that mass and energy are interchangeable, meaning that even a small amount of mass can release a tremendous amount of energy. This principle forms the foundation of nuclear energy and explains why stars emit so much light and heat through nuclear fusion. In nuclear reactions, tiny amounts of matter are transformed into vast quantities of energy. This equation also led to predictions about antimatter and other exotic forms of matter, enriching our understanding of particle physics and cosmology. Despite its success, relativity isn't without challenges. General relativity, which describes large-scale phenomena like stars and galaxies, doesn't align well with quantum mechanics, which governs atomic and subatomic particles. The pursuit of a unified theory that combines both realms, often called the theory of everything, is one of the biggest goals in theoretical physics, with approaches like quantum gravity and string theory attempting to bridge this gap. Furthermore, general relativity's predictions about black holes and singularities hint that our understanding of space-time might still be incomplete. Observations of phenomena like dark energy, which accelerates the universe's expansion, suggest there are aspects of physics yet to be discovered. Though it may seem abstract, relativity has practical applications in everyday life. For instance, the Global Positioning System, GPS, relies on relativity-based adjustments, as satellites orbiting Earth experience different gravitational and speed effects on time. Without these adjustments, GPS accuracy would quickly degrade. Relativity also plays a crucial role in particle accelerators, which must account for relativistic effects as particles approach light speed. The Large Hadron Collider, for example, uses these principles to ensure the accuracy of high-energy particle physics experiments. In summary, the theory of relativity transformed how we perceive the universe by demonstrating that space and time are interconnected, and can be influenced by gravity and motion. General relativity redefined gravity through space-time curvature, while special relativity reshaped our understanding of time, speed, and energy. Together, these theories form the backbone of modern physics and continue to inspire new technological and scientific advancements. But relativity is only the beginning. As we venture further into the mysteries of black holes, time travel, and the expanding universe, we may yet uncover even more mind-bending truths about reality. Let's move on to string theory, an ambitious and mathematically complex theory that aims to unify all of the fundamental forces in nature and provide a theory of everything. String theory suggests that the fundamental building blocks of the universe aren't particles like electrons or quarks, but incredibly tiny, vibrating strings. These strings and their vibrations supposedly give rise to all particles and forces, making string theory one of the most promising yet confusing approaches in modern physics. At its core, string theory proposes that the building blocks of our universe are one-dimensional strings. Each string vibrates at a specific frequency, producing different particles and forces, similar to musical notes on a string instrument. For example, an electron and a photon would both be different vibrational patterns of a fundamental string, much like different notes produced by the same string on a musical instrument. One of the revolutionary aspects of string theory is its potential to unify quantum mechanics, the physics of the very small, and general relativity, the physics of the very large. While quantum mechanics explains the behavior of particles and relativity explains gravity, these two frameworks are currently incompatible. String theory could provide a way to reconcile them by offering a single, coherent framework that accounts for all known forces and particles. Multiple versions of string theory emerged in the 1980s, leading to confusion. However, physicist Edward Witten introduced M-theory, uniting these versions into one overarching framework. M-theory suggests that strings may not be the only fundamental structures. Higher dimensional objects called branes, short for membranes, might also exist. These branes could be as small as a single point or as vast as a universe, adding a whole new layer of complexity to the theory. According to M-theory, our own universe might be a three-dimensional brane floating within a higher dimensional space, possibly interacting with other branes and universes. One of the most challenging and mind-bending aspects of string theory is its requirement for additional spatial dimensions. In everyday life, we experience 3 dimensions of space and 1 dimension of time. However, for string theory's equations to work, 10 or even 11 dimensions are required. The additional dimensions in string theory are hypothesized to be compactified or curled up so small that we can't perceive them. Imagine a 2-dimensional sheet of paper curled into a tight spiral. If you zoomed out far enough, it would appear as a 1-dimensional line. In a similar way, the extra dimensions in string theory could be curled up to scales smaller than an atom, making them invisible to us. The idea of extra dimensions, while mathematically sound, is almost impossible to visualize, adding to the confusion and intrigue surrounding string theory. These dimensions could hold the key to understanding forces that seem weak or mysterious in our familiar dimensions, such as gravity. Because string theory allows for many possible solutions, there may be an enormous number of vacua or possible configurations of the universe. Each configuration would correspond to a different set of physical laws and constants, leading to the possibility of a multiverse, an immense collection of universes, each with its own distinct properties. In other words, our universe could be one among countless others, each governed by different rules. This idea is both intriguing and problematic. If the multiverse is real, it would be impossible to test or observe directly, meaning we may never confirm or falsify its existence. Critics argue that this makes string theory difficult to treat as a true scientific theory, as it may lead to predictions that cannot be tested or observed. Despite its promise, string theory faces challenges. It lacks testable predictions, is mathematically complex, and some question if it qualifies as a scientific theory due to its non-falsifiable nature. Even without concrete proof, string theory has profoundly impacted physics and mathematics. Concepts from string theory have influenced quantum field theory and pure mathematics, leading to insights that extend beyond its original scope. Physicists continue refining string theory, hoping that future experiments or new technology will reveal supporting evidence. String theory offers a path to unify all fundamental forces, potentially revealing a theory of everything. Whether it leads to a revolutionary understanding or paves the way for future theories, string theory marks a bold step in our quest to unravel the cosmos mysteries. Now, let's explore the next mind-bending concept: quantum mechanics. This theory explains the behavior of particles at microscopic scales, where classical physics no longer applies. Quantum mechanics introduces us to a world governed by probabilities, uncertainties, and phenomena that challenge our understanding of reality. One of the cornerstones of quantum mechanics is wave-particle duality, which suggests that particles like electrons and photons can behave both as particles and as waves. In the classic double-slit experiment, particles fired at a barrier with two slits create an interference pattern, behaving like waves. However, if we observe which slit each particle passes through, they act like particles again, as though the act of measurement changes their behavior. This mysterious link between observation and reality questions the very nature of existence. Next, we have the uncertainty principle, proposed by Werner Heisenberg in 1927. It states that we can't know both the exact position and momentum of a particle at the same time. The more precisely we know one, the less precisely we can know the other. This isn't due to measurement limitations, but is a fundamental property of quantum particles, adding an element of randomness and unpredictability to the quantum world. Imagine you have a ball moving along a path. In classical physics, you can measure both its speed and position accurately. However, in quantum mechanics, if you try to measure an electron's exact position, you inherently alter its momentum, making precise measurement impossible. Quantum superposition takes uncertainty a step further. It states that particles can exist in multiple states simultaneously until observed. Erwin Schrödinger famously illustrated this with a thought experiment: Schrödinger's cat. Imagine a cat in a sealed box with a vial of poison. If a radioactive atom decays, the vial breaks, killing the cat. Until we open the box, the cat is in a superposition of being both alive and dead. This paradox highlights how observation affects outcomes in the quantum world. Superposition has practical applications, especially in quantum computing. Quantum computers utilize qubits, which can exist in multiple states at once, allowing them to perform vast amounts of calculations simultaneously. This gives quantum computers the potential to solve complex problems far beyond the reach of classical computers. Quantum entanglement is one of quantum mechanics' strangest phenomena. When particles become entangled, the state of one instantaneously affects the state of the other, no matter the distance. If we measure one particle, we instantly know the state of the other, even if they're light years apart. This phenomenon, called spooky action at a distance by Einstein, challenges the idea that objects are only influenced by their immediate surroundings. Entanglement has significant implications for quantum communication and cryptography. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum systems exist in superposition until observed, causing them to collapse into one definite state. This raises profound questions. Does reality depend on consciousness? If observing a particle can change its state, what role does our mind play in shaping the physical world? This interpretation bridges physics with philosophical debates about the nature of reality. In contrast to the Copenhagen interpretation, the many worlds interpretation proposes that all possible outcomes of a quantum event actually occur, each in a separate universe. For example, in Schrödinger's cat experiment, one universe would have a live cat and another would have a dead one. The many worlds interpretation implies a multiverse of branching realities, each representing different outcomes, avoiding the need for wave function collapse. While it sounds like science fiction, this interpretation has gained popularity among physicists. Quantum mechanics has led to groundbreaking advancements in technology, especially in computing, cryptography, and telecommunications. Quantum computers, for example, use qubits that can represent both 0 and 1 simultaneously, enabling them to solve complex problems much faster than classical computers. Quantum cryptography uses entanglement to develop unbreakable encryption methods. Quantum teleportation, although not teleportation in the science fiction sense, uses entanglement to instantly transfer information, potentially revolutionizing secure communications. Quantum mechanics presents philosophical and scientific challenges that stretch beyond physics. Unlike the deterministic world of classical physics, the quantum world introduces probabilities, where outcomes depend on observation, challenging ideas of objective reality. Quantum mechanics has inspired numerous interpretations and debates. Is reality independent of observation, or does our consciousness shape it? These questions bridge the realms of science and philosophy, making quantum mechanics one of the most existentially provocative theories. To summarize, quantum mechanics defies conventional understanding with concepts like wave-particle duality, uncertainty, superposition, and entanglement. This theory challenges classical physics, introducing a probabilistic and interconnected universe that pushes the boundaries of what we know. Quantum mechanics has paved the way for technological breakthroughs in computing and cryptography, yet leaves us questioning the nature of reality itself. As we journey deeper into these mysteries, quantum mechanics will continue to shape our understanding of the universe and invite us to rethink reality. Thank you for joining me on this cosmic voyage. The universe is not just something out there, it's a part of us, and we continue to explore it. We learn more about ourselves. If you enjoyed this exploration, share your thoughts and questions in the comments below. What part of the universe fascinates you the most? Let's keep the conversation going. Don't forget to like, subscribe, and click the bell icon to receive updates on our latest videos. Together, let's continue to unlock the mysteries of the universe.